In this fourth chapter in our course on statistics, we will learn about the Central Limit Theorem. Now, in the previous chapters, we learned that by computing sample statistics, we always introduce uncertainty, because these sample statistics will always be an approximation of the underlying population statistics. Now, quantifying this uncertainty is the name of the game in statistics, and one of the primary components in doing so is the Central Limit Theorem. Now, in this brief chapter, we will cover this theorem by using one of the tools that we learned in the previous chapters, namely simulation. And by doing so, we will get a more visual and intuitive understanding of this crucial theorem in statistics. So let's get into the slides and see what we will learn. In this first lesson, we will start out by learning about the basic idea underlying the Central Limit Theorem. In particular, we will look at what distribution it actually talks about. Then we will bring this into practice with some hands-on simulations, where we also generate these nice figures that will help us get a better understanding. We will do so with normal populations, and then in the next lesson we will extend or generalize the Central Limit Theorem to non-normal populations. And then we will end this chapter with looking at some limitations of the Central Limit Theorem. Before we learn about the main idea behind the Central Limit Theorem, let's discuss its importance and why it is so central in statistics. Apart from being one of the main reasons that the normal distribution is so ubiquitous, the Central Limit Theorem is actually the underlying mechanism of why the p-value works. Now, because in later chapters we will cover the p-value in great detail, it is important to already understand the underlying mechanism why it actually works. So let's now cover the main idea behind the Central Limit Theorem. And let me start by reading you the definition that can be found on Wikipedia. Now, this definition will probably sound quite vague, but it will be worthwhile at the end of the chapter to come back, read it again, and then you will see that it will make much more sense. So here's what it reads. In probability theory, the Central Limit Theorem states that, under appropriate conditions, the distribution of a normalized version of the sample mean converges to a standard normal distribution. This holds even if the original variables themselves are not normally distributed. There are several versions of the Central Limit Theorem, each applying in the context of different conditions. So this is quite a mouthful, and it is quite vague. So let's see if we can do better. Now, another approach to the Central Limit Theorem is to delve into the mathematics, because the Central Limit Theorem is a very mathematical theorem. But as is the case in this course, we will not go into the mathematics. Instead, we will use our favorite tool, namely to simulate. But before we go into this and delve into the code, we will look at what the distribution is that the Central Limit Theorem actually talks about. So let's cover the different types of distributions that we already know. And in fact, there are three levels of data distribution. The first one is the population distribution. It's the dataset that contains all of the data points of your entire population. Now, as you already know by now, this is a theoretical and inaccessible distribution. Only to us it is accessible because in this course we generate it ourselves. Now, of course, this population distribution has some statistics assigned to it, namely the mean and the median and the standard deviation. The second level of distribution is the sample distribution. Now, remember, a sample is a randomly drawn subset from the underlying population, and therefore it has much less data points. Now, even though it has fewer data points, we can still bring them together in a histogram. And this histogram then showcases the distribution of our sample data. Now, as was the case for the population, the sample data also has some statistics attached to it. We have the sample mean, the sample median, and the sample standard deviation. Now, as we know by now, the sample statistics are only approximations of the underlying populations. And in fact, if we take another sample, another randomly drawn subset from our population, the sample statistics of that particular sample will most likely be different from the first one. Now this difference in sample statistics brings us to the third distribution, and actually the data distribution that the central limit talks about. This is the distribution of sample statistics. Now, as I said, and as we clearly saw in the previous chapter, every sample has a different sample statistic, because every sample is a new random subset from our underlying populations. So if we take together all of these sample statistics from our different samples, then they themselves will exhibit a distribution. So this is quite abstract and in words. So let's look at it in a more schematic way. Now let's say that we start with a population distribution of 100,000 data points. This will be our first level of distribution, our population distribution. Now from this population, a number of samples can be randomly drawn. Let's say that we have one sample of 40 points, another sample of another 40 points, and a third sample of 35 points, and so on. Now, because our population has so many data points, we can draw a lot of different samples from our population without ever drawing the exact same sample twice. And this is our second layer of distribution. Each sample has its own distribution. Now, the next step is that for each sample, we can compute its own sample statistic. For instance, here, for each sample, we compute the mean, and this will result in one number for each sample. Now, if we take all of these numbers together, that means that we have another data set of sample statistics, and a data set can be brought together in a histogram and thus comes with its own distribution. And it is this new distribution that is our third level distribution. And it is this distribution that the central limit talks about. So now that we have a clear understanding of the different levels of distribution and what distribution the central limit actually talks about, let's start and simulate this. And to do so, we of course visit our trusty notebooks. Now, in this notebook cell, we won't be encountering any new code. All of the code here we already encountered in previous cells. The only thing here is that we bring it together in a different way so that we can simulate such a complex scenario. The first step is to generate our populations, our first level of distributions. Our population size will be 100,000 points. And then we generate two populations. In the same way as we did before, we use numpy.random.normal to generate random numbers according to a normal distribution. The first population will be centered around a mean of 1, the scale or the standard deviation will be 0.5, and the size will of course be 100,000 points. The same for population 2, but only here we will have a mean of 2. Now the lines of code below this are commented, because they are for the next lesson, but you can already see that they are very similar. We also define populations, but now with some other distribution functions. And this is already a heads up for the next lesson. We skip immediately to the part where we sample our populations. Now we need to keep in mind what we're actually trying to do here. Now that we have our two populations, what we want is to draw a lot of different samples from these populations, and for each sample, compute the sample statistic, in this case the mean. Now we want to collect all of these sample statistics together and then visualize these statistics in a histogram. And this will give us our third level of distribution, the distribution of sample statistics. So what we first do is we define the number of samples that we want to draw from these populations. In this case, we take 10,000 samples, and this immediately shows the strength and the power of our simulation tool. In reality, it would be impossible to generate 10,000 samples from an underlying distribution. If you could do this, then you would just pull them all together into one large sample. But here we can just simulate it. Next, we define the number of data points in each sample that we will draw from our population. In this case, we take 20. In the next step, we will define and initialize our Python arrays in which we will store and collect our sample statistics. One statistic for each sample. Now, because we will generate 10,000 samples, these arrays will need to have a length of 10,000. Now, how do we do this? Well, we define it as being numpy.zeros, and then the number of iterations. And what this does is it creates a Python array with all zeros, but the length of this all zeros Python array will be the length that we provided, in this case 10,000, such that we have one index for each sample statistic. We do so for sample 1, for sample 2, but also here already we will define a Python array with the same length but with the name mean diffs. And let me get to later why we do this. Now all of the magic of our simulation happens in these lines of code, the for loop. Now what does this for loop do? Well, first of all, the contents of this for loop are called 10,000 times. Why is this? Well, because we do for I in range number of iterations, and number of iterations is 10,000, the number of times that we want to draw a sample of our population. So each time we first of course define our two samples, one for each population. And this is done in the exact same way as we did in the previous lessons. So sample 1 will be a Python array with 20 random numbers drawn from population 1. And the exact same of course can be done to generate sample 2, where now we draw 20 data points from population 2. Then the next step is to compute the sample statistic for each of the two samples that we just generated, and then to store them in the Python array that we initialized and that contains all of the other sample statistics of the other samples in our for loop. And to do this, we define the ith element in our Python array to be the numpy.mean, so the mean of sample 1. And the same for the Python array containing the statistics for sample 2. The ith element will be equal to the mean of sample 2. And to end off, we see this mean diffs Python array come back. We define the ith element in this Python array as the difference of the sample statistics between our two samples. So in our case, the difference between sample 1 and sample 2. And we store it in this Python array. And after this for loop is complete, we are left with three new Python arrays. We have sample 1 means, being a Python array containing all of the sample statistics or the means of samples drawn from population 1. We have sample 2 means containing all of the means of samples drawn from population 2. And then we have means diffs containing all of the sample mean differences from sample 1 with sample 2. So now we want to visualize these three Python arrays. And to do so, we will again make histograms. Of course, we first define our figure and our axis. And in this case, we need a subplot with 3 rows and 2 columns. In the upper left panel, which is axis at position 0, 0, we visualize the histogram of population 1. We again use 30 bins and set density to true. We give it a title, histogram population 1. In the panel to the right of that, the upper right panel at position 0, 1, we visualize the same histogram, but now for population 2. And of course the color is also different. Then we want to visualize the sample statistics, in this case the sample means for both sample 1 and sample 2. And to do this, we again just make a histogram. But this time, instead of making a histogram of population 1 or population 2, we give it the Python array containing all of the sample means. So for sample 1, we have sample 1 means, again with 30 bins, density is true. And for sample 2, we do the exact same thing, but now for sample 2 means, and again 30 bins, and density is equal to true. Now in the bottom panel of this subplot, we again do the same thing as in the previous lesson. We merge the two panels together to make one big plot on the last row. And on this plot, we will make the histogram of the mean differences. Remember, this is the Python array containing each difference between the means of samples. So each time the mean of sample 1 minus the mean of sample 2. And this will again give us a histogram with 30 bins and density is equal to true. When we now run this cell, we see that in under 1 second, the entire simulation is run and the visualizations are made. Now this means that in under 1 second, we draw 10,000 different samples from our two populations, and for each sample, we calculate the sample statistics, in this case, the mean. So let's now look at these visualizations that we created and see whether we can observe the emergence of the central limit theorem. The first row of figures represents the population histograms. Now, these are very familiar by this point, and we see a nice normal distribution for population 1, which is centered around the value of 1, and a nice normal distribution for population 2, which is centered around the value 2. In the second row, we find our histograms of our sample statistics, and there are a few things that we can say about them. First, the number of data points that make up each of these histograms is exactly equal to 10,000, because each data point represents a sample statistic that we computed in our for loop. The second thing is that we can immediately observe that these distributions are normally distributed, or at least approximately so. And this is exactly what the central limit theorem says. It says that the distributions of the sample statistics of an underlying population will converge towards a normal distribution. And it goes even further than that. It says that additionally, these normal distributions are centered around the population means. And this is also something that we can see. We see that for our first distribution of sample statistics, that it is centered around the value of 1, which is indeed equal to the mean of population 1. Likewise, for our second histogram, the histogram of sample 2 statistics, that it is centered around the value of 2, which is also, of course, equal to the mean of population 2. And in this way, we have arrived at the central limit theorem by first generating our own populations, and second, using simulation to draw tens of thousands of samples from these populations. And this uncovers a truly extraordinary feature about statistics. Even though you don't have access to the population data, and thus the population statistic, and each time you draw a sample from this population, you will sometimes get a sample statistic that is larger than the population one, and sometimes you'll get a sample statistic that is lower than the population one. If you take all of these sample statistics together, then the average of these sample statistics will approximate the underlying population statistic incredibly well. The third thing that we can learn from these sample statistic histograms has to do with representative samples, something I talked about earlier. Because these histograms show the distribution of sample means, they show that indeed most of our samples are representative, in the sense that if you would compute their mean, it would be approximately equal to the actual mean of our population. This is the bulk of the histogram, where these data points have a mean of, let's say, 0.9 or 1.1. However, we also clearly see that there are some samples which have a much lower mean or a much larger mean. For instance, here we have some samples that have a mean of 0.7, which is 30% lower than the actual mean of our underlying population. And then these, of course, constitute the extreme samples. And it is also this principle of extreme samples that will be at the heart of the p-value that we will learn in later chapters. And talking about the p-value, this is exactly where this last graph comes into play. Again, this last distribution shows the difference of means of each pair of samples. So if we have two samples, then we compute their mean and we subtract them from one another. Now we see that the distribution of the difference of sample means is centered around -1. And this again makes sense in light of the central limit theorem. Because if we take the mean of population 1, which is 1, and we subtract the mean of population 2, which is 2, we indeed get -1. However, because we know that some samples have other means than 1 for population 1, and for population 2, if we draw samples, some have other means than 2. This is basically why they have a distribution around this mean. If we then subtract these two sample means, we will also get a distribution of differences. And in this way, we have combined the distributions of two samples, and thus from two populations above them, into one distribution. and this will be the core of the p-value, looking at the distribution of differences of different samples of populations. But more on that later in detail about the chapter on p-values. Now, of course, as with all of the notebooks, I strongly recommend that you go back and you change some of the numbers. You can, of course, change the populations and see how this changes the figures. Now, you could also change the number of samples that we simulate, or you could change the number of data points in each sample. But this would lead us to the limitations of the central limit theorem. And that is something that we will see in the next lesson. Now, going back to the slides to conclude this lesson, you might object that the only reason that these sample statistics histograms on the second row here are normally distributed is because their underlying populations are normally distributed. However, this is exactly the strength and the power of the central limit theorem. It says that these sample statistics histograms will always approximate a normal distribution even when the underlying populations are not normally distributed. Now, of course, you might or might not believe that when I just say it to you, and therefore, in the next lesson, we will actually simulate this scenario such that you can see it for yourself and thus experience the real power of the central limit theorem.